Okay, we'll start with the chapter of ray model of light. So first things first, light has a certain property, which is basically the parts that is underlined over here. So light is a form of energy itself. It travels at this speed in vacuum. So this is 300, 1, 2, 3, 1, 2, 3 meters per second, and this is space. Okay, and light doesn't require a medium to travel. So this word propagate itself just means the word travel. So this means that light from the sun, which travels all the way from outer space, can reach us on Earth. This is something that we're all familiar with. And we learn that light travels in a straight line over here. Okay, so there is one thing to add. It's usually from the image to the eye itself. Now, this one, you can just read it on your own. When you're answering the question, we don't need to actually include this part that is actually in brackets. This one will actually be relevant to what we'll actually be learning later when we're actually drawing all the different ray model diagrams. Okay. Now, normally light, when you have one singular light, is what we call a light ray. Okay. And a group of light rays itself is what we call it as a beam of light. Okay, so a beam of light is just a group of light rays. So normally we'll actually just only draw about 3 light rays to show all the light rays that is represented. So in between all of this, there's actually countless numbers of light rays in between them. It's just that so that it doesn't look very, very messy. Normally we just use the maximum, minimum, and somewhere in the middle. So for our light beams itself, our group of light rays, we have 3 different types. We have your divergent beam, which means that they are all gonna spread out. You have your convergent beam, where they're all gonna focus to a point. And you have your parallel beams, where they are all parallel to one another. Okay? So next, apart from that, you also have a few terms that you need to know. Your luminous object means that it can produce its own light. And your non-luminous object, which basically cannot produce its own light. Okay, so the very, very easy or the very, very standard examples that they use is basically the sun versus the moon. Now, even though we have the term moonlight itself, the moon itself actually doesn't produce its light. Whatever light that you actually see from the moon is actually what we call a reflected light. Basically, the moon will actually reflect light from the sun so that we can actually see the moon itself. Okay. Now, next page, you have your opaque objects and your shadows itself. Now, if you notice this little light bulb over here, this is a very small light bulb. So if you were to notice, for example, right now you're sitting in the room itself, all of your lights that is in the room itself, they're relatively large compared to this very, very small light bulb itself. So if you notice, if you have a very small light bulb, you tend to have a very sharp shadow that you see, a very dark shadow. You won't see like fading shadows or like blurry shadows itself. You'll see a very, very dark shadow image. But for example, if you just raise your hand against the wall, you'll notice that the shadow that you cast upon the wall itself will actually be a little bit blurry, and it's not, you might see even like different layers upon one another. So this is basically if you have a very small light source, you will have a sharp shadow. But if you have a large light source, you will actually produce a blurry shadow. Okay, so let's say if we take the sun, for example, if you notice the light rays of the sun, they will actually be blocked by the moon itself. Notice that the moon is over here, that your light rays, they will be blocked by the moon itself, and therefore it will actually cast a very, very dark shadow, which is highlighted in green over here. This very, very dark shadow is what we call a solar eclipse or a lunar eclipse. And if you notice this part that is extremely dark, this is what we call umbra. Okay, umbra, if I'm not wrong, is Latin for shadows. So this one basically means shadow. Shadow or dark. Okay, then you will notice that some parts of your light rays will actually be traveled and actually still be blocked by the moon, but you'll notice that it actually casts a larger shadow around this area itself. Now, this area is also a shadow, but it's not as dark as the green color spot over there. So we'll call this a penumbra. So pen means not so. So this means not so dark shadow. Okay, now just take note, not all schools actually cover this portion. So if your school does cover this portion itself, just take note, the top of the sun will be blocked by the top of the moon, and the bottom of the sun blocked by the bottom of the moon to form your umbra. And then the reverse will actually form your penumbra over here. For other parts of the earth, they will actually be brightly lit. Okay. So normally, whenever we have a light ray, now if you notice, your light ray itself, they will just look like a singular arrow, correct? So if there's nothing blocking your light ray, it will simply just travel in a straight line. However, if let's say I have a surface that is being introduced, there are a few things, there are three things that can happen. First is what we'll learn later on, which is your reflection itself. Your light rays will actually bounce off a surface. So first thing that can happen is reflection. Second thing that will actually occur is what we call refraction. Okay, this pronunciation is very, very similar, but it's slightly different. So when you have refraction itself, instead of going in a straight line, you will actually bend towards or bend away from the surface. So you just take note, there will be a slight change. We'll cover more on that in the next video. So last but not least is that you actually be absorbed. So basically when you actually go in, you just be absorbed at the very surface over there. So this is where we talk about the colors of light for the last part of the light chapter. Okay, so let's take a look at the reflection component. Now, reflection means the bouncing off of light rays. The singular F, bouncing off light rays. So you can see over here, for your laws of reflection, you actually have two of them. So this one is quite a standard question that they always ask, especially for your first part of the question. They'll ask you, state the laws of reflection. Okay, so for the first law itself, the incident ray, reflected ray. Now, your incident ray is this ray over here. So you can just imagine the word incident just means incoming. So it's the one that is approaching the surface. So incoming ray is what we call your incident ray. So remember I and I, incident ray. Then after that, it will be reflected after it hits the surface. And this is what we call your reflected ray or your outgoing ray. Okay, normally we just call it incoming or, incident ray and reflected ray. Then you will notice this magical word over here. Now, this is using a dotted line. Normally, to represent this normal itself, normal just means 90 degrees to surface. So we always try to draw using a ruler, hang on, take out my ruler. Using a ruler itself, you should have 3 dotted lines. Now, normally I'll draw 3 dotted lines, 1, 2, 3 above the surface and 1, 2, 3 below the surface itself. Where do we actually draw your normal? We'll draw it where the light ray will actually hit the surface over here. So the moment this incident ray hits this surface, I'll draw a normal at every surface that has a light ray. Okay? So just do take note. Now this normal is very, very important because of the second part over here. You'll notice that we have a few new terms, which is angle of incidence I and your angle of reflection R. So what is these angles about? Now these angles are actually the angle from your incident ray, between your incident ray and the normal itself. It's always going to be next to your normal. So it's very, very important. You will see that your normal is one of the most important parts of your light ray drawing itself, and same last but not least, your angle of refraction is the same. It's also on the right beside your normal, between your reflected ray and your normal itself. Now, why is this very, very important? Is because, for example, the school questions, they like to give you this. You have a incident ray because it's incoming, right? And they'll actually give you this. If this is 30 degrees, what is I? So how do we do this kind of question itself? Simply, we take out our ruler. We know that this is a surface itself. We're going to draw 1, 2, 3, 1, 2, 3 over here. We know that it's going to be reflected away. But first, what is my angle of reflection? You will see that your angle of reflection is this part I over here. It will never be between the surface and your incident ray. It's always beside your normal and your incident ray itself. So I is just simply 90 degrees minus 30 degrees, which is 60 degrees. Okay, so if you notice, our angle of incidence, I, is the same as my angle of reflection, R. So what this means is, if I just repeat this, you'll notice that I will form my angle of reflection. I'll call this R as well. So this I and R, they are the same. Both will be 60 degrees. So do take note about that. So when you draw this, you'll notice that your normal is your line of symmetry. So if you flip this over, this will be the exact same number. And this also means that this is 30 degrees. Okay? So do take note, your normal is very, very, very important. We always try to draw your normal at the very first step. Okay? Now, let's take a look at the work example over here. Now, like I said, every time you hit a surface, we will draw your normals first. So if you have a ruler, make sure that you use the transparent part of your ruler itself and try to align it based on the surface over here. So you can see what I've just done. I'll use the division over here to draw my 3 dotted lines on top and below itself. So if you have a protractor, you can actually measure it, and you'll notice that this is roughly about 30 degrees. And you measure your angle of incidence I, and when you draw it, it'll be like this. So you can see that they are very, very symmetrical. Now, you don't have to use a protractor unless the question asks you to measure or specify exclusively. If it was just a sketch, please use a ruler and a pencil itself to roughly get the same shape and size so that they are roughly symmetrical in shape. Okay? Now, normally when we have circular surfaces itself, the radius is your normal. So what does this mean? So from the X, which is the center, you're going to draw a dotted line all the way to the surface that you see over here. So 1, 2, 3, all the way up. Make our life easier. So this will be I, and this one will be roughly, like I said, if you're not going to use a protractor to measure it, it should roughly look like I and R, they are roughly the same. So you do the same for the very last step, which is about here. 1, 2, 3, 1, 2, 3, 1, 2. So you can see roughly it is about like this. And we'll just continue from there. Now, if you notice all of the light rays that I have been drawing, I have the arrow itself. If you omit the arrow in your working itself, you actually be penalized 1 mark. So do take note, which is your I, which is your R. I is basically coming towards the surface, so your arrow is towards the surface. R is moving away, so you move away from the surface itself. Okay? Next, questions can also ask you to calculate the angles, like which is what I did just now earlier on. So you can do exactly the same step. First, our very first step, whenever we deal with any kind of light ray diagram, is to very first draw your normal. So 1, 2, 3, 1, 2, 3. So this is R, because this, you can see the arrow is coming inwards, right? This is my incident ray, and this is my angle of incidence. So they ask us to complete the ray diagram as well. So we know that I and R, they are the same. So first thing, what is I? I will just be 90 minus 60, which is 30 degrees. So show some working, don't just put in the numbers. And since I and R, they are the same, they will also be 30 degrees. So if you want to be a little bit more specific, 30 degrees, you have this part over here. I and R is 30 degrees as well. Okay? Next. Now, normally when we draw our normal itself, we only focus on the very first surface that you touch. This is your surface, and that is your incident ray. So very first surface itself, we're gonna take your ruler itself, align it based on this, and take your pencil, and we'll draw 3 dotted lines up, 3 dotted lines down. Okay, so we can see that this is I. But the thing is, we need to do a little bit of math before we can actually do to that step. So first thing, we know that this is 90 degrees. So this one, by default, if you use sum of angles in the triangle, this is 60 degrees. Same thing, this is a 90 degree as well. So now, focus on this line that you see here. Angles in a straight line is 180 degrees. So 180 minus 60, you get 120 minus way 90. You'll notice that your angle of incidence I is also 30 degrees. Okay, so I and R, they are the same. It is still going to be 30 degrees. So same thing, last but not least, let's draw our refracted ray. So draw it out. This is R. As you can see, it's a little bit messy over here. So that's why we need to label everything nicely. Whenever you're drawing anything, always make sure that you label all of your components properly and nicely. If you have very untidy handwriting, sometimes you get penalized if the marker can actually see it wrongly. Maybe your angle looks like an arrow, they might actually penalize it. So do draw your things nicely and as legible as you can. Now, last but not least, this is one of the trickier questions. Now, if you notice, the first surface is this diagonal line over here. So our incident ray and our normal itself, when we draw it, you'll notice that they are actually aligned to one another. 1, 2, 3, 1, 2, 3, correct? So if you notice over here, normally your eye is like this. So if this gets smaller and smaller, smaller and smaller, smaller and smaller, you'll notice the eye becomes, it will actually approach 0, correct? So at this point where your incident ray is parallel to your normal, your eye is actually 0 degrees. So over here, I is 0 degrees, I and R, they are the same. It is also going to be 0 degrees over here. So because of this, how does your light ray actually travel? Now, if this is a mirror, your light ray, kind of like a ball bouncing, right? You will actually just bounce backwards. So you actually travel back the same line over here. You just travel in a line backwards. It's like dropping a ball onto the ground. It moves. When you drop the ball, it goes down and then it bounces back up. So same thing, when you hit the surface, you actually bounce backwards back to the origin, according to the original path that it takes. All good? Let's move on. So there are actually two types of reflection. You will have your regular reflection, the one that we always see, and what we call your diffused reflection. Now, if you remember some parts of your science itself, you might learn about diffusion. Now, normally when we say diffusion, it means spread out or basically dispersed through all parts of the room and stuff like that. So very similarly, your diffuse reflection, you can see over here. Now, both of the scenarios in this case, both of them have parallel incident rays. However, the moment you hit the surface, this is where it gets different. Okay, so let's take a look at this first. This incident ray, same thing. If you want, you can actually just take note. When you draw your normal itself, 1, 2, 3, 1, 2, 3. Your I and your R, they are the same. Okay, so if you do all of this, they are exactly the same. That's what we have learned just now. So what does this mean? It means if you have a smooth surface, you can see the surface is very horizontal, right? Smooth surface, what does that mean? When you have a smooth surface, you will have regular reflection. So what does that mean? So regular reflection means you will see a clear and sharp image. So you'll see a very nice sharp image that you have over here. So Let me just shift my ruler to a side, and you will see a clear image form. You have regular reflection. It is a mirrored or a smooth surface. Okay, so basically your diffuse reflection will be the exact opposite. However, one thing I'm just to tell you is that whatever we learned just now, your laws of reflection, I and R, they are still the same. Let me prove it to you. Now, if you notice over here, when your light rays actually hit, hang on, when your light rays, let's say the middle one over here, this one, okay? When it actually hits the surface, now your surface is no longer no longer flat, right? So when you actually take your ruler itself and try to align it, you'll notice that your normal is now no longer vertically upwards. So 1, 2, 3, 1, 2, 3. If you were to go and measure it and if you draw it properly and correctly, you'll notice that your angle I and your angle R, they are still the same. I and R, they will still be the same. This is the law of reflection. As long as you see reflected, this will always be true. Okay? So what does this mean over here? So whenever you have any kind of rough or jagged surface that you see, so this word matte, it means rough. Okay? So what happens? You will have either no image form or you will have a blurry image form. Okay, so over here, if, let me just use green color, rough surface, what does it mean? You will have diffused reflection. If you have diffuse reflection, what does that mean? You will have blurry or no image form. Okay, so all of this, you need to take note. Now, in some cases itself, the question will actually tell you the end result. They'll tell you, hey, I can see a clear and sharp image. So what does that mean? Because I can see a clear and sharp image, it means that my light underwent regular reflection. So there must be a smooth surface. So sometimes you might need to work backwards based on the results that you actually see. So if you see a clear image, a sharp image, you will have smooth surfaces to have regular reflection. So sometimes you might need to actually work backwards. Okay, so now, images and mirror itself. Now, what exactly is an image? Now, for example, if you are just staring at the computer screen, right? There is nothing between you and the computer screen itself. So what happens? Your light, remember, light always travel in a straight line. Okay? This is something that we learn, but it's always now from the image to the eye. Okay? Just remember, just to recap, the parts in bracket, you should not write it during your exam. It's mostly in your own head when you repeat to yourself. Light always travel in a straight line. So if there's no mirror or there's no surfaces blocking you, you will see the object and the image at the same position. The object is here, your image is also here. So you just draw a single straight line. This is how you see the image and the object itself. Okay, but the moment you have a mirror over here, for example, if you're right now, if you go to your toilet or basically your wardrobe, you'll notice that the image that you see, for example, your clothes and whatsoever, the image that you see is normally in a straight line, because if you stare directly at the mirror itself, the image is where you will see, you will notice it is a straight line. But in reality, your object is actually not inside the mirror, it's outside the mirror, right? This is why you will see that your object is over here. You will actually hit this surface. And if you were to put your ruler here and draw your normal, 1, 2, 3, 1, 2, 3, you'll notice that your angle I and angle R, they are the same. Remember, now this is just a tilted version of what we normally see. So just take note, our image is where we think, our minds itself, they think where the actual, they think where is the image seen is, but in reality, the object is actually outside the mirror. So the mirror world is all a lie, it's all a trap. This is what you think it is, but the real object is actually nearer to you at this side. Okay, so do take note about this. And basically, the light rays always travel towards our eyes. They will never travel from the eye because we don't shoot laser beams out of our eyes itself. It's always from the object into our eyes. That's why if you stare at the computer screen for too long, or you stare at your handphone screen for too long, your eyes gets a little bit tired out and you will need to take a short break. Okay? Now, characteristics of your plane mirror image. So this is basic characteristics of my mirror image itself. Now, normally, if you really forget all of these characteristics, you can actually just go to the toilet and you can just play around with your mirror itself. Now, so these are your characteristics. So what does it mean by virtual? It means not real. Okay. Now, normally if the question asks you, which is a very, very common question that they always ask you, they ask you, what is meant by a virtual image? Please do not say that it is not real. Okay. A virtual image is an image that cannot be captured onto a screen. Okay. And some schools, they like to actually flip it around. They'll actually ask you, okay, what is a real image? If you were to flip it around, a real image is an image that can be captured on a screen. Okay, so the only difference is virtual is cannot be captured onto a screen. Real is it can be captured on the screen. It's basically the opposite of what you see over here. Okay, then next you have what we call upright. Now, if you look into the mirror itself, the top of your head and the top of the mirror image's head is the same. Top and top is the same. Bottom and bottom is the same. So for example, if you were to stand here and you stare into the mirror itself, your image will also be like this. Top to top, bottom to bottom. They are still the same. However, if you were to notice itself, if you raise your left hand, okay, this word laterally means left to right. Inverted means flipped. So left to right, flipped. If you were to raise your left hand, the mirror image will actually raise their right hand. Go take a look at the mirror itself. You can actually play around with it. You'll notice that it is actually flipped this way. Your left hand is the mirror image's right hand. Okay? And even though the object may appear a little bit smaller than yourself, you will notice that it is actually the same size as you. If you were to measure your own height, and if the mirror image were to measure their own height, they'll actually be exactly the same. Okay? And then last but not least, this is one of the proper characteristics that will actually allow us to remember or basically allow us to draw your mirror ray diagrams. So for example, if I have a mirror here, okay, normally if you see this line with a lot of slashes, this is what we call mirror. So your image, let's use this triangle as an image itself. We know that your distance from the mirror is the object. So this is my object. So I'm trying to find my image. So the image and the object, they are the same distance apart. So what we're going to do is we're going to measure this distance D over here, which is 90 degrees. So once you found this distance D, you'll notice that the image is exactly the same distance away. So what we're going to do is, instead of using solid lines, we're going to use dotted lines to represent your image that you have. So they will actually be equidistant apart from the mirror. So same thing, you can think of the mirror as your line of symmetry. So if you were to flip this, you'll notice that they are the same. And take note, the bottom part of the image, which is the flat part, is facing the mirror at the same side. So when you flip your image, do take note it is left to right flip based off the mirror. If your mirror is up down, then it will flip downwards. Okay, do take note about this. So for example, let's do the work example together. So take out your ruler first. We are gonna measure this. First thing, your X is your object. So we're gonna measure this distance over here. Okay, I think that's one. So this one will be this distance over here. So we're going to measure this distance. And since I'm using OneNote, it's a little bit difficult to measure. I'm just going to copy paste. And you'll notice that over here, I'm going to put away my ruler. You'll notice over here, when you actually draw the distance D, can you see that we are only using the surface on this side? Okay, so when your light ray itself only touches this surface, we need to just use this surface. We don't use the middle of the mirror. We don't use the right-hand side of the mirror. We use the very, very first surface that you touch. This is your mirror. So over here, what this means is at this point, this is my image I. Okay, do take note, this must be 90 degrees. Next, second example over here, you'll notice that our mirror is a little bit short. So what you can do is you can take your ruler and just take note, this part over here, because this mirror, nothing exists above here. Dotted line to represent the extension, but that in reality, there is no mirror over there. So same thing, we're going to take 90 degrees and we will want to measure this over here. This is our distance, D. So same thing, we're going to repeat it on the other side as well. Make sure that you use the same line and you'll notice that your image will be over here. Same distance apart. Okay. Last but not least, we do the exact same step, just that this one involves a little more trick. Extend out the mirror. Do take note, it has to be 90 degrees to your surface. So roughly like this. It's going to be 41. Okay, so what we want to do is measure this distance. Label it as D. And we want to find this exact distance over here. Put away my ruler. And you can find that your X is right at this spot. Okay. Now, for your mirrors itself, if you notice, all the mirrors that we have previously been using have all been flat mirrors. So those flat mirrors are what we call plane mirrors. These are typically the ones that we use most of the time. So do take note. For example, if you will use your flat mirror itself, we can actually use it to bounce off your light rays very, very easily. You'll notice that your light rays will just travel in a very nice straight line, 90 degrees to one another. For your periscope, which we use in submarines and for other purposes. So these are your plane mirrors. For your convex mirror and your concave mirror itself, they are basically opposites of one another. So there is a little typo over here. It should be concave. So you can just imagine the word cave in means you can link it as it zoom in. So like for example, if you zoom into your object, you'll notice that you can see things more clearly, but you can see less things, right? So you'll see that your image that you see is previously small. Now you see it is now bigger. So the purpose is to magnify your objects, to make it bigger, larger images. Okay? And in reverse, your convex mirror itself, it is instead of zooming in, we will want now to zoom out. So when we zoom out, what can you do? You will see that your image becomes smaller, but you can actually see more things now. So because of this, your convex mirror is for you to see things more clearly from different perspectives. So you can see things, see more things, but they are a little bit blurrer or less clear. Compared to when you zoom in, it becomes clearer, but you now see less things. Okay? So now, let's talk about your drawing parts over here. So you can see in this diagram over here, the steps are actually labeled below. So let's take a look one by one. So every time you just see this, you have an object, you have a mirror, the very first step, without even thinking, most of you can actually just straight away, I need to find my distance D first. Once you find your distance D on the object side, you want to do the exact same step on the other side as well. So once you find this, you can find my, hang on, and find my image on this side. Okay, so this will lead us to your second part over here. Now, remember the line that I said earlier on. Light always travel in a straight line from your image to your eye itself. So normally, if we are expected to draw more than one light ray itself, we will actually start from eye, the letter I, and we'll actually have to draw all the way to the top and bottom of eye itself. So what happens is anything inside the mirror, they are all virtual, they are all fake, they are not real. So we'll use dotted lines for it. Once we come out, solid lines. So put an arrow here. Do the same for the other side, all the way to your bottom part of your eye. So do the same step here. Dotted lines. Once you touch the mirror, solid lines down, arrows. Okay. Now, if you notice, this is not the final step because what actually happens in real life? In real life, you notice that your light rays will actually travel from your object because remember, light will only be reflected when it hits a mirror itself. So what happens here is that it will travel, touch here, and we do the same for the bottom part as well. So basically, it's just connecting the dots. Now, if you notice, the lines are very, very close. So if you were to draw like this, it is very, very close. Some teachers might actually penalize it. So just do a small gap. So at least you show that there's two different arrows, two different directions to show that your steps are drawn correctly. So with this is the final answer for your light ray drawing. Because some students actually stop at this part, you'll notice that you actually still need to draw. So you can show that your light rays actually travel from here, hits the surface, and it will bounce and travel into the eye. So same thing for the bottom side as well. Now, if you notice, why do we draw to the top and bottom of the eye? Because actually in between all of these two light rays itself, there's actually millions and millions of light rays in between. So this top and bottom of the eye just refers to the minimum and the maximum part of what we can actually see, the image over here. Okay, so last but not least, let's do your checkpoint 3. Okay, so instead of giving us the object and the image itself, the question now gives us two light rays that is being reflected. So remember, what is the line? Light always travel in a straight line from the image to the eye. So if we were to take this light ray and draw this backwards, we can actually find that. So just draw all the way through, and you do the same for the bottom side as well. Just take a ruler and try to make it nice. Dotted line all the way through. You'll notice that there is a point where your light rays will intersect, and this point where it intersects is what we call your image. So once we find the image, we do in reverse. Let's find the distance D. So once we find the distance D over here, hang on. So once we find distance D, we're gonna do the exact same step to find your object. So just that everything now is in reverse. So D, and you want to find your object O. So this is not the last step. Don't forget, we need to connect the dots. So let's draw the last part in. Solid line here, because this side is the real world. This is the mirror world. So everything inside should be dotted line. Last but not least, our last step. Over here, don't forget, we need to draw arrows. Okay, so with that, we have done our drawing. You can see that your object is here, image is here. For the parts behind, if you feel that it's a bit untidy, you can just clean it up, but don't erase everything. Show the step of your line of intersection. So with that, we have come to end for your reflection parts.